Betelgeuse. The red Goliath star on the brink of catastrophe. Betelgeuse, a colossal red supergiant star, is a remarkable object in our galaxy. If it were positioned where our Sun is, its surface would extend out to the orbit of Jupiter. This enormous star is not only massive but also unstable, poised for a catastrophic explosion that could forever alter the night sky. Astronomers have recently detected alarming signals from Betelgeuse, utilizing the James Webb Space Telescope. Noted scientist Brian Cox has issued a stark warning. Could we witness a cosmic explosion that will change our view of the heavens for eternity? The mystique of Betelgeuse. In the vastness of the universe, stars are born, live, and die in astonishing ways. Recently, one star has captured the attention and concern of both astronomers and the public. Betelgeuse, a red supergiant located in the Orion constellation. This ancient star is incredibly massive and has long fascinated observers with its striking reddish hue and varying brightness. Recent developments have intensified interest in Betelgeuse, suggesting we may be on the brink of a significant event in its life cycle. But what do these changes mean? Are we witnessing the onset of a cosmic spectacle of immense proportions? Betelgeuse's size and life cycle. Betelgeuse is roughly 1,000 times larger than our Sun, a size that is almost beyond human comprehension. Imagine a star so enormous that if it replaced our Sun, its surface would extend beyond Mars' orbit, engulfing Mercury, Venus, Earth, and Mars. This immense size not only illustrates the physical majesty of Betelgeuse, but also highlights its stage in the stellar life cycle. As a red supergiant, Betelgeuse is nearing the end of its life, having exhausted the hydrogen in its core and begun fusing helium. The age and evolution of Betelgeuse. Estimated to be between 8 and 8.5 million years old, Betelgeuse is relatively young in human terms but ancient by cosmic standards. Over millions of years, it has undergone dramatic changes, evolving from a hot blue star to the red giant we observe today. Currently in its final stage as a red supergiant, Betelgeuse's evolution is marked by the ongoing battle between nuclear fusion and gravitational forces. Another fascinating aspect of Betelgeuse is its unique reddish color, which results from a cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is around 5,500 Kelvin, Betelgeuse's temperature hovers around 3,500 Kelvin, allowing it to emit light at wavelengths that appear red. This color is more than just aesthetic. It provides insights into the star's physical condition and the processes occurring within its vast gaseous envelope. Historically, Betelgeuse's color has changed over time. Ancient records from Roman and Chinese astronomers indicate that Betelgeuse appeared yellow several centuries ago. By the 9th century, Arabic astronomers began noting its red hue. This historical transformation reflects the star's evolution and the remarkable lifespan of celestial objects. The great dimming of Betelgeuse. Another intriguing feature of Betelgeuse is its variable brightness. As a semi-regular variable star, its brightness fluctuates periodically, a phenomenon that has captivated astronomers for centuries. Betelgeuse undergoes a regular cycle of brightness changes approximately every 5.9 days, alongside a more extended cycle every 5 years. This cyclical dimming and brightening, first documented by Sir John Herschel in 1836, has been observed in various cultures for ages. What truly sets Betelgeuse apart, however, is not just its brightness variations but also their unpredictability. Unlike many stars that dim in a consistent manner, Betelgeuse sometimes deviates from its established pattern, hinting at complex and not fully understood processes within its enormous structure. Recent observations and concerns. Recently, astronomers were taken aback by a sudden and significant change in Betelgeuse's brightness. This dramatic dimming, referred to as the Great Dimming, raised numerous questions and concerns. In late 2019, Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to dim unexpectedly. By February 2020, it had lost so much light that casual observers noticed the difference. The challenge in monitoring Betelgeuse's activity lies in the fact that light from the star takes time to reach us. When we observe Betelgeuse, we are seeing it as it was in the past, approximately 725 years ago. This time delay complicates our ability to predict and analyze rapid changes in its behavior. Andrea Dupree, the deputy director of the Center for Astrophysics at Harvard and Smithsonian, and her team closely monitored Betelgeuse as part of a 3-year study focused on tracking changes in its outer atmosphere. They employed the Hubble Space Telescope to gain insights into this massive star's behavior. Their observations provided valuable information about the workings of variable stars like Betelgeuse, revealing that these stars often expand and contract, leading to changes in brightness. Using Hubble's ability to capture ultraviolet light, researchers analyzed spectra taken at different times in 2019 and 2020, which showed the movement of material in Betelgeuse's upper atmosphere. They discovered that material was being ejected from the star's surface at an astonishing speed of about 200,000 miles per hour. This hot, dense material ultimately traveled thousands of miles away from Betelgeuse, forming a dust cloud that obscured the star's light during the dimming event. Dupree and her team estimated that during this eruption, Betelgeuse expelled approximately double the amount of material than expected from its southern hemisphere. While all stars gradually lose mass over time, Betelgeuse's mass loss was particularly noteworthy due to its rapid rate, much faster than the Sun's. This situation led astronomers to speculate whether this event could indicate an impending supernova explosion, especially given the scale of the mass ejection and the resultant dimming. The potential for a cosmic explosion from Betelgeuse, presents an intriguing opportunity to observe a celestial event remarkably close to Earth. However, the central question remains: what does this dimming mean for Betelgeuse's future? Is it a sign of an impending supernova, or merely a transient phase in the star's extensive life? Several theories have been proposed to explain this sudden change in brightness. One widely accepted hypothesis suggests it may represent a precursor phase in the supernova process, gaining traction due to the belief that Betelgeuse is nearing the end of its life. Another theory posits that dust, potentially originating from the star itself, could be obstructing our view. It's known that red supergiants like Betelgeuse shed material, which can accumulate into a dust cloud thick enough to obscure the star's light. A third theory explores how alterations in the star's photosphere, the visible outer layer, could influence its apparent brightness. Researchers tackled this mystery through a combination of observational techniques and detailed analysis. Spectroscopic studies indicated a significant drop in Betelgeuse's surface temperature, suggesting the star might be dimming due to the presence of a large dark spot. This decrease, measured at around 170 Kelvin during the dimming event, supported the idea of substantial changes occurring on the star's surface. The Hubble Space Telescope, often referred to as humanity's guardian in space, played a crucial role in unraveling this surprising phenomenon. Its observations indicated that Betelgeuse's dimming was likely caused by a substantial amount of hot matter being expelled into space. This material formed a dust cloud that obscured about a quarter of the star's surface light from reaching Earth. The dust cloud was believed to consist of hot plasma expelled from a large convection cell on the star's surface. As this plasma moved through Betelgeuse's hot atmosphere toward its cooler outer layers, it formed dust grains that blocked light. Hubble's ultraviolet spectroscopic studies, initiated in January 2019, were essential in understanding the events leading up to Betelgeuse's dimming. These studies identified dense hot matter traveling through the star's atmosphere well before the dimming occurred. Ground-based telescopes also detected the decline in the star's brightness in December 2019, with Hubble's findings confirming these observations and providing deeper insights into the expelled material. The revelation that Betelgeuse was losing material at a significantly faster rate than previously believed led to important implications for our understanding of stellar evolution, particularly concerning red supergiants. Notably, Betelgeuse is not the only star undergoing such dramatic changes. Historical supernovae like SN 1054 and SN 1987A have provided valuable insights into stellar deaths and the formation of new cosmic materials. These earlier events have helped shape our understanding of how stars die and their effects on surrounding space. For instance, SN 1987A, which occurred in a neighboring galaxy, offered a close-up view of a supernova explosion and its aftermath. Such events contribute to the cosmic cycle by dispersing heavy elements and influencing star formation. If Betelgeuse ultimately becomes a supernova, it would create a dazzling display visible from Earth, potentially brighter than the Moon and possibly even observable during the day. Such an occurrence would provide a unique opportunity to study the final stages of a massive star's life and the formation of cosmic structures, as well as the distribution of heavy elements across the universe. Despite the dramatic nature of a potential supernova, the vast distance between Betelgeuse and Earth offers a significant buffer, ensuring that such an explosion is unlikely to harm our planet directly. The insights gained from observing Betelgeuse's transformation will continue to enhance our understanding of stellar evolution and cosmic phenomena. The role of red supergiants in cosmic evolution. Red supergiants like Betelgeuse are crucial for understanding cosmic evolution. These stars represent the final phases of massive stars before they undergo supernova explosions. Their large size and relatively short lifespans make them ideal laboratories for examining the end stages of stellar evolution. Red supergiants significantly influence their surrounding environments, as the energy they release during their final stages contributes to the formation of heavy elements essential for planet and life development. Nucleosynthesis and heavy element formation. The process of nucleosynthesis in red supergiants involves transforming lighter elements into heavier ones over their lifetimes. These stars fuse hydrogen into helium, then helium into carbon and oxygen. As the star approaches the end of its life, it attempts to fuse even heavier elements, resulting in the formation of elements like iron and nickel, which are expelled into space during a supernova. These heavy elements enrich the interstellar medium, contributing to the formation of new stars, planets, and potentially life. Studying red supergiants like Betelgeuse helps researchers comprehend the processes that produce these essential elements and their distribution throughout the universe. Implications for cosmic science. The eventual explosion of a red supergiant and its resulting supernova has significant implications for cosmic science. When Betelgeuse detonates, the heavy elements it has formed over its lifetime will be dispersed across the galaxy. This distribution plays a critical role in the chemical evolution of the universe, affecting the structure of new stars and planetary systems, as well as the potential for life. By studying these processes, astronomers gain insights into the history of our universe and the conditions that led to the formation of planetary systems and habitable planets. Observational methods in supernova research. Understanding supernovae and their progenitors involves a variety of observational methods. Telescopes capture different light frequencies, optical, ultraviolet, and X-ray, providing valuable information about these celestial events. The James Webb Space Telescope, for instance, has enhanced our ability to observe distant and faint galactic objects, revealing remarkable details about the early stages of cosmic evolution and supernovae. Ground-based telescopes also play a crucial role, providing continuous monitoring and contributing to our understanding of variable stars and supernovae's effects on star-forming regions. Conclusion. The explosion of a red supergiant like Betelgeuse can have profound effects on its surrounding star-forming regions. The shock waves generated by a supernova can trigger the formation of new stars by compressing nearby gas and dust, a process known as triggered star formation. This interaction between the shock wave and the interstellar medium further contributes to the dynamics of the cosmic ecosystem, influencing the distribution of matter and energy throughout the universe. Overall, observing Betelgeuse's potential transformation provides a unique opportunity to deepen our understanding of stellar evolution, the life cycle of heavy elements, and the intricate workings of the cosmos.